Barnhart is honored to present the winning 2023 SC&RA Rigging Job of the Year for the $150,000 to $750,000 category. At Barnhart, we are known for taking on extremely challenging projects, and one of our favorite parts of any challenging job is the sense of achievement we feel upon completion. Our entry is a lump sum project that took place at a chemical plant in the Southeast in April 2022. 1 year before the project was executed, we began visiting this customer and were asked to review a challenging project. As shown in the picture, the project involved replacing a 50-foot reactor leg that was clogged and weighed 12,000 pounds. Our objective was to replace the clogged reactor leg while minimizing the outage window and avoiding the removal and replacement of the upper reactor. Upon reviewing the project, we recommended a laser scan to explore solutions. Our initial scope was to remove and replace the 12,000-pound clogged 50-foot length inner reactor leg. The plant had purchased new legs that could be installed as a single 50-foot piece or as two separate 25-foot sections bolted together once in the structure. The existing leg was a 50-foot long piece. To minimize the outage window and avoid the need to remove and replace the upper reactor, the plant requested that we explore all options. There were 4 major constraints of this project. The job site was congested with multiple contractors planning activities in the vicinity, so managing the available area was critical to the project's success. This job had never been attempted before, so there were a lot of unknowns in method and schedule. The legs, which are surrounded by the structure on all sides, do not have an easy or direct way to pull them out without removing multiple obstructions. None of the inner reactor legs directly under the reactor had ever been replaced in 50 years. The plant management team was concerned that there would not be enough time in the outage to complete the project. Saving every hour possible was critical, and reducing the schedule for this project to the point where it would no longer be that the critical path was considered impossible. Shown here is the project job site. From top to bottom, you can see the reactor at the top of the structure pointed out. The direction the legs need to exit the structure per Barnhart's alternative rigging plan, the main crane location, the cantilever beam staging location, and the reactor leg staging location at the bottom of the picture. Once again, due to the congested site, it was necessary to plan every step of the job meticulously to ensure that we would not interfere with other ongoing outage activities. After processing the laser scan, our engineers used the resulting data to plan the project. We held meetings with the plant's engineers to determine which structural members would be the easiest to move and to identify any interferences that might be involved in the different methods for removing and replacing the inner legs. This is our initial plan to replace the clogged 50-foot inner leg that was jammed with catalyst. Our solution was to utilize our moving counterweight cantilever beam, which was engineered to reach under the structure and connect to the reactor leg with a welded lug pinned off to our system. We would then choke the upper flange of the leg and use a chain fall to tilt it to the correct angle so that it could clear any obstructions as we lifted it upward and out. The customer planned to flush the legs with acid during the upcoming outage, but this method failed to clear the catalyst jam, resulting in leaks developing in all 12 reactor legs. Plant management decided to replace all 12 reactor legs during the next outage, which was the largest and most complex outage ever attempted at the plant. 4 months prior to the outage, Barnhart and the contractor were brought in to walk the job down and begin planning for the outage. Barnhart worked with the contractor to create schedules comparing the conventional method of removing the upper reactor to the alternative method of taking the leg sections out through the side. During the planning phase, the contractors pointed out the difficulty of welding a lug to the legs during the outage and how much time it would take. Considering that these legs were classified as ASME pressure vessels with specific welding criteria and inspections required, in response, Barnhart assigned an additional research and development engineer to look into an alternative method of connecting the cantilever beam to the reactor legs while the project engineer continued his work to plan the other portions of the project. This is the initial concept developed by our research and development team, showing a manipulator arm designed to wrap around the leg and be bolted securely. Once this new component was developed, our engineers incorporated it into the laser scan model to demonstrate the solution. To hold the vertical load, we utilized 2 chain falls and straps, while 2 hydraulic cylinders allowed for rotation of the reactor leg from vertical to horizontal. The tool was equipped with an independent motor and pump, running off the onboard generator, which allowed for remote operation of the reactor leg tilt mechanism. The customer was highly satisfied with this method and issued a purchase order for immediate development of the tool. Barnhart had a 2-month time frame to complete the engineering, order required materials, fabricate, load test, paint, and ship the tool to the site to be ready for the outage. During the material ordering process, many hydraulic fittings, the pump, and main load cylinders had to be upsized or replaced to utilize parts that would be available locally within the required time frame to meet the customer's schedule. After the new manipulator was fabricated at our fabrication shop, we load tested it using a structural pipe left over from a previous project. Our engineers developed a new standard operating procedure for the tool. An engineer then traveled with the tool to train the local team on how to use it before mobilizing to the site. As shown in the site layout, the work area was highly congested. To streamline the process, we brought in a secondary crane so we could work on each side of the structure simultaneously. One larger crane removed the inner legs on one side with the cantilever beam, while the other smaller crane worked on the outer legs on the opposite side of the structure without the cantilever beam. After each side was completed, the cranes switched sides until all inner and outer legs were removed and replaced. This required careful planning and coordination with the customer to avoid interfering with other outage operations in the vicinity. Our engineers utilized the 3D laser scan to develop a comprehensive 3D solid model that depicted each step of the operation and simulated the movements. They worked closely with the plant's structural engineers and contractors to plan which obstructions would need to be removed during the lifting operation. In the model, our cantilever beam is shown connected to the first inner upper leg to be removed. The beam would be brought in, and the back of the manipulator would be closed tightly around the leg. All thread bolts would then be used to close the sleeve firmly around the leg. Once the sleeve was secured, the straps and chain falls would be tightened to hold the leg in a vertical position. With the leg rigged tightly, the contractor could begin cutting the center to allow the upper 25-foot section to be shifted to the side and cleared from the upper structure. Once shifted to the side, the leg is tilted and safely removed. The upper section was removed and placed horizontally on the ground for staging. The manipulator was used to safely down-end the upper section to a horizontal position without requiring the use of a forklift or secondary crane. This helped keep the lifting area clear of personnel, and it was faster. The next step involved bringing in the cantilever beam and connecting it to the lower section of the pipe. The sleeve was then bolted around the leg and securely rigged in place. The leg is lifted upward, tilted to the proper angle, then lifted upward and out. Now the lower section is out and down-ended to horizontal to stage. To avoid painting ourselves into a corner in the congested area, we had to work our way into each side and remove the inner 3 legs on each side. Once we removed the inner legs on one side, we installed the new legs in the same manner and then shifted to the other side of the structure. Throughout the operation, it was vital to maintain a connection between either an outer leg or inner leg and the bottom 180-degree bend. This connection allowed the contractor to simply support the alternate side with a chain fall and not waste time disconnecting and rigging it back into place before replacing the leg. This was a carefully planned project, with every step discussed and agreed upon in meetings with the contractor, plant management, and Barnhart. Our engineering, project management, and field supervision teams collaborated closely to ensure that every movement was meticulously planned. It was important to locate spotters and tag lines to guarantee the safety of all personnel and to maintain the appropriate level of control during each lifting operation. We would like to highlight some of the engineering challenges that were overcome during this project. Within a tight time frame, we were able to swiftly modify an existing tool that had been in use for many years to meet a unique requirement for one of our customers. During the rotation of the reactor leg, the engineering team had to consider the shifting CG location of the system. To level the system throughout the operation, they had to plan for adjustments to be made to the cantilever moving counterweight. This was achieved with the help of two independent operators who used remote controls while communicating with the crane operator and outside spotters via radio. We were able to adapt to the customer's changing requirements by designing and fabricating a new tool that enabled us to connect to the leg without welding and without the need for a secondary crane or forklift. We completed the job ahead of schedule, thanks in part to the implementation of the new Barnhart tool. This innovation provided the customer with an option that was previously unavailable, resulting in a significant reduction in their schedule from 14 days to just 7 days. By employing a laser scan, we were able to plan the work with precision and collaborate with the customer to identify the most efficient path forward. This also enabled us to confirm that our plan would be effective in the field, similar to getting to do the job virtually on the computer prior to executing in the field. We would like to emphasize some safety bullet points from the job. At the beginning of each shift, we held a meeting with the outgoing and incoming crews to discuss the necessary steps to be taken during the upcoming shift. During the meeting, we reviewed the engineered plans and any associated risks. We also discussed ways to mitigate any identified risks or safety concerns that were raised during the previous shift. Once the job hazard analysis was finished, the team inspected our equipment and rigging to ensure that they were in an acceptable condition to proceed with the job. Any issues that were identified were addressed prior to the commencement of work. No accidents, incidents, or injuries resulting in lost time occurred during the course of this project. Prior to beginning the work, the engineer conducted a training session with our crew on the new tool. During the session, they reviewed all the necessary details and procedures that must be followed during operation. A Barnhart qualified risk manager was appointed to oversee the job and monitor the plan at a high level in the field. Their responsibilities included ensuring that the engineering plan was followed and that any modifications were properly communicated to the appropriate channels for approval. Prior to commencing the job, we spent time to establish a clear communication plan. This included identifying spotters and tagline operators, assigning radio control to specific individuals, and coordinating the various operations required for the project. We also ensured that we had enough personnel to provide the necessary oversight to safely carry out the lifting operations. We would like to point out some general highlights from the project in closing. Utilizing this alternative method, we reduced their schedule from 14 days to 7 days, taking our project out of the critical path for the outage, which was extremely valuable to the site's project management team. Our connection to the customer and our expertise in rigging opened a new path forward to the customer and introduced previously unknown solutions to their complex problem. We removed the risk of having to remove the reactor head to access the inner legs, which would have taken an unknown time and introduced risk to the project during the reinstall that might have extended the outage. Our alternative plan reduced the risk from bull rigging the legs, utilizing many chain falls and rigging points to drift them in reach of the crane, and kept labor in safe areas away from the lifting operations during the critical lifts. It took 394 engineering hours and 2,301 field man hours to complete this project. The job was completed safely with no accidents, incidents, or recordable. In conclusion, this was a challenging project that required extensive planning and collaboration with the plant and our contractor. We are proud of our work and excited to share our experience with you. Thank you.